speakers today need no introduction, but let me still introduce Pavel Pudlák. And if you did anything with proof complexity or with SAT circuit, you've seen Pavel's name over and over and over again. And from lower bounds, from feasibility calculation, I think your name is on most lower bounds in proof complexity that I can think of. Cutting planes, the similar result as lower bounds for cutting planes. From the point of view of mathematics, Pavel has a great book called Mathematics of First Order Arithmetic, and a more recent book, which is a gentle introduction to logical foundation of mathematics and complexity. It's gentle, but it still talks about a lot of really advanced concepts that Sasha mentioned. Also, if you do algorithm for SAT, probably the most well-known algorithm for SAT, exponential algorithm, is PPAZ. And again, this is Pavel's work. So many things that I can't even mention all of them, circuit complexity, other connections. So I'd rather let Pavel talk about this and the beautiful connection between different areas of complexity and SAT. Please.
Thank you, Antonina, for a very flattering introduction. So my talk will be hopefully short and definitely very elementary. I will not talk about new stuff. I will actually talk about it that I have already spoken a couple of times, but each time I still find some details that I can present in a better way or complement things in it. So I'll start with some background from the foundations of mathematics. We use various theories to formalize arithmetic or set theory. These theories are of increasing strength. Here on the slide, we have T2, which is bounded arithmetic. So I should have also included S12 that was mentioned before, which is a fragment of T2. Then we have a fragment of Peano arithmetic called I sigma 1, which is induction for sigma 1 formulas. A stronger theory than that is than Peano arithmetic is the so-called second order arithmetic, which is not arithmetic formalized in the second order proof calculus, because there is no any, but it's an extension of Peano arithmetic by sets, subsets of interpreted as subsets of integers, non-negative integers. Then Zermelo-Fraenkel theory, and we can go on by adding new axioms such as strongly inaccessible cardinal or the existence of measurable cardinals, and obtain stronger and stronger theories. And these theories are stronger. We can prove that they are stronger because of Gödel theorem. And they in fact prove more true pi1 sentences, assuming that these theories are true, that they describe the true true sentences of arithmetic. But the question that is interesting for us is whether they prove more sentences relevant to computational complexity. This is what we would like to know. So this is one thing that we can ask. And another thing is, if we take some theories that differ in a way like P differs from NP and NP differs from sigma 2P and so on, then we can ask whether these theories form an increasing hierarchy. And this is open and probably very difficult problem because here we cannot apply Gödel's theorem. Of course, we cannot prove that we cannot apply the theorem, but we know one thing, that the consistency of these theories is so strong that none of these theories prove the consistency of the weakest one. So we cannot use the consistency to separate these theories. Here's an example of what I am very much interested in. Given a problem and an algorithm that solves P, what is the weakest theory that proves the soundness of A? By the soundness of A, I mean that the algorithm solves the problem. Or given a problem and a time bounty, you can ask what is the weakest theory such that for some algorithm T proves that A solves P in time T. Here's an example that appeared in our paper a long time ago. If factoring is hard, then the theory denoted by S12, which Sasha mentioned briefly, does not prove the soundness of any polynomial time algorithm for primality. So we are in the situation that we do know that there is a polynomial time algorithm for primality, but assuming a reasonable conjecture, S12 doesn't prove the soundness of this algorithm. So it's conceivable that, that there are algorithms that are so complex or tricky or use deep mathematics that they are not provable in weak systems of arithmetic or set theory. So for instance, here we are not able to prove the soundness of AKS algorithm in any fragment of T2. But at the same time, we don't have a reason to believe that it is not provable in T2, except that we don't know how to do it. But there may be ways to argue that it's not possible by placing these things into a hierarchy of total function and P problems. But I am a bit digressing. So here's what I mean by soundness of an algorithm. So we have to be careful how we formalize these questions. We can always formalize an algorithm so that ZFC or any fixed theory does not prove the soundness. We can just embed the consistency statements of this theory into the algorithm, and then we are not able to prove that it is sound. But we can ask the opposite question, or something formally opposite. Is it possible to formalize every algorithm that its soundness is provable in Peano arithmetic or some other fixed theory? Now, this question is vague, and unfortunately, I'm not able to formalize it in a way so that it doesn't have a trivial answer. But this is what I would be very much interested. So instead, I will show today some related things that are not exactly this question, but of the same nature. What I'm going to present is something that can be presented as syntactic classes versus semantic classes. Syntactic classes do have complete problems, while semantic classes usually do not. We usually are not able to prove that there is no complete problem, but we can argue that there are some good reasons to believe that there are no complete problems. And what I'm going to talk about is three conjectures or several conjectures that are on the form that saying that there are no complete problems in certain classes. Russell Impelazzi doesn't like the word conjecture because he suggests to call things hypothesis, but in this case, it's something that I very much believe that they are true, that we should eventually be able to prove it, like we believe that P is not equal NP. So we don't say that P equal NP is a hypothesis.
Pavel, what is
Yes?
a semantic? Can you define semantic class?
Okay. A semantic class is a class that is defined in such a way that we have to prove the defining condition that that the problem belongs to the class. So, for instance, P is a syntactic class because we can present every polynomial algorithm in such a way that we know from the code that you write down that it runs in polynomial time. This is not the definition is not syntactic, but if you put into the code of the algorithm a clock that will stop the algorithm after polynomial number of steps, then we know for sure and that it will stop after polynomial time. The dog makes noise here. I will have to do something. But other classes, typically randomized classes, are not of this form. You write down an algorithm and you accept this as a definition of a set in this class if you prove that it accepts the input with certain probability or not. Sorry, I have to make a short break to see what's going on.
The dog doesn't have a mute button?
No. Okay, so he's now quiet. Okay, so let's go on.
No, my question is, when we use semantic class, we're actually very loose about it. Because I can always ask, when you say all the algorithms in some run in some time, I say, in what set theoretic universe are you talking about? So my claim is that when we use semantic classes, we are really very loose. And if we try to be precise, we will have to be better defined and to say in what class of models are we talking about.
Well, I don't understand this. So I think that the semantic class is defined precisely like RP, BPP. Of course, they may be equal to P, and then they are not semantic anymore because they can be defined syntactically, but otherwise they are semantic. So excuse me. Okay, sorry. So this dog is very clever. He can open the doors, so it's difficult to contain him somewhere. So anyway, this is not a precise definition, but we will see examples, and maybe it will be better to look at the examples that I will present. Is it okay, Moshe?
Yes, Sasha just gave a good answer. I'm happy with his answer.
Okay. Yes, maybe.
So just to say, Sasha said in the chat, semantic, there is no recursive enumeration of machines computing languages from this class.
Say it again.
Semantic, there is no recursive enumeration of machines computing languages from this class.
Yes, yes. The reason why we do have complete problems in syntactic classes is because we can enumerate the algorithms. Of course, it may not work always because the enumeration may be not so effective. But this is just a rule of thumb. It's not a precise statement. So let's get to examples. So the first item on my list or in the title is the set of tautologies. So let's restrict to DNF tautologies, but this is not important, just to be more concrete. We have proof systems, and a proof system is something that is complete, that there is a proof for every tautology, and sound that it doesn't prove non-tautologies. The completeness is easy to ensure by embedding some well-known proof system into it, and then say if we believe that the resolution is complete, then we can add to each proof system resolution, and then we know that it is complete based on the assumption that resolution is complete, and we don't have to prove essentially anything. But the soundness is a problem. So if you have a very strong proof system, then you have to prove that it is sound. It's not, it may be a non-trivial thing. So this is how they are defined. And then we have polynomial simulations. I'll not define them because we know this very well, that you can, if you have one proof system and the other proof system simulates this proof system, it means that you can simulate the proofs of one system in the other. So there is polynomial time function that translates proof system from one into the other. And the conjecture is that this condition of soundness is indeed syntactic, that we cannot prove it easily, which means that there is no consistent theory that proves the soundness of all proof systems. So this may be one possible statement of this conjecture, and which is not maybe completely obvious, but easy, that this is equivalent to the condition that there is no proof system that simulates all other proof systems. I will call this optimal proof systems. An optimal proof system is that simulates all proof systems. And also I am omitting the specification polynomial. So simulates means polynomially simulates effectively, that you have polynomial time computable functions. I will not talk about the length of proofs.
Your red syntactic should be semantic, right? What did you say, syntactic?
Also, yes, this should be semantic. Thank you. Yes. I have a kind of selective blindness. I cannot proofread my slides very well. And this conjecture is...
Your slides are semantic, not syntactic.
So, okay, and this conjecture is a fairly strong conjecture, because in particular it implies that exponential time is not equal to non-deterministic exponential time, and this is probably stronger than p is not equal to np. There is a related class, which is the class of disjoint NP sets. So this class consists of pairs of sets, A, B, which are in NP, and they are disjoint. Again, we can define polynomial reductions between two elements of this class. This is quite natural. We can use either Turing reductions or many one, which means that if we have two pairs, then the first set should be mapped into the first set of the other, and the second should be mapped into the other. So this is something that you can easily imagine. And now the condition that these two sets are disjoint is a semantic condition. I have to be careful not to confuse the two things. Semantic because if you write down the definitions of these sets, you don't know whether they are disjoint unless you write down some trivial thing like all the sets in A start with bit 0, all the sets in B start with bit 1. So these are easily recognizable, but it's easily recognizable that they are disjoint, but in general, it may be hard to prove that they are disjoint. So we can state the conjecture that there is no complete disjoint NP pair. And this conjecture, again, is equivalent to the statement that there is no consistent theory that proves the disjointness of all disjoint NP pairs. Now, I'm stating this conjecture, at least the second part is stated a bit not quite precisely, because what does it mean that the theory doesn't prove that a pair is not disjoint? Whether the theory proves that the pair is disjoint definitely depends on how you formalize these pairs. So you need to write down a formula if you want to talk about its provability. So to state this precisely, one would need to say that it does not prove the disjointness of all NP pairs. However, you formalize the pair. So you take the best formalization for which it should be the easiest way to prove that they are disjoint. And for this, you are still not able to prove it in some theory. I mean, you're still not able to prove it in the theory. All right, so how these conjectures are connected. To show that they are connected, one can use the very important concept of canonical pairs of proof systems. If we have a proof system P, then the canonical pair of the proof system, as defined by Sasha, consists of the set of basically you can view it as formulas that have short proofs, but to be more precise, what we use, we are using padding that limits the length of proof. So it's a pair of formula and a number represented in a unary, such that phi doesn't have phi has a refutation of length at most n. And the second set is basically SAT, but we need something that looks similar to AP. So we also use padding, but it is just a padding that does nothing. So this pair somehow captures the strength of the proof system. Because if P simulates Q, then the pair corresponding to Q is polynomially reducible to pair corresponding to P. This is very easy to prove, And the corollary of this is that the conjecture about disjoint NP pairs implies the conjecture about proof systems for propositional tautologies. Now let's get to total function NP. So TFNP means total function NP, which I define in the following way. A problem in total function NP is given by a binary relation that is computable in polynomial time and a polynomial bound, such that the relation defines multi-valued but total function. That is, for every a there exists b, which is at most polynomially longer than a, such that it satisfies the relation. So this polynomial bound is given just to be quite precise, but typically the polynomial bound is already implicit in the relation R. So I will often omit this polynomial bound and talk only about the relation. The problem associated with this relation, which has this property, is to find for a given a to find b such that it satisfies the relation. So now again, this condition is semantical. If you have a definition, if you have a formula for R or a polynomial time algorithm computing this binary relation, you never know for sure that this defines a total function. So you have to prove in some theory. Now again, we have reductions between these problems. Now I will just use R and R prime for these problems. And these relations, this reduction are defined in the obvious way. We have either many-one relations or Turing relations, and it makes no difference for the conjecture that I'm going to state. So this many-one reduction is given by two polynomial time computable functions, f and g. So you want to compute a witness for a in a relation R, and you can do it in such a way that you first compute fa and find a witness for R prime, and from this witness b and a, you get the witness for a in relation R. But it may be more complicated to just using Oracle for the solution of R prime. Anyway, so we have a class and we have reductions, and then we can ask whether there is a complete problem. But let's just take an example so that we are sure that this concept is not empty, that there are probably total function NP that are not solvable in polynomial time. Because if everything is solvable in polynomial time, then everything will be reducible to everything. So then there will be a complete problem. So factoring is an easy example of a problem that is not solvable in polynomial time, but it's based on the assumption that it is hard. So the hardness of factoring simply means that this total function NP problem is not believed to be computable in polynomial time. So we have at least two different types of total function NP problems: those that are solvable in polynomial time, and those that are not. The conjecture about total function NP is much stronger than than just saying that there are problems that are not solvable in polynomial time. The conjecture is that there is no complete total functional NP problem. So this is far more stronger than saying that, that there is one problem that is not solvable in polynomial time. And again, this can be stated equivalently in logic, that there is no consistent theory that proves totality of all total functional NP problems. These are, of course, hopeless conjectures because they imply P and QNP. So do we have any reasons to believe that they are true? One reason why I believe this is true is that it's very much like computable functions in provably total computable functions in theories. If you have increasing theories with increasing strength, then you can show that also the class of provably total computable functions increases with the strength of the theories. It does not have to always increase, but at least in the examples that I showed at the beginning, this is the case. So the only difference here is that in total function NP, everything is polynomial, while here it is computable. So this formal similarity is one reason to believe that it may be true. The other reason is that we already have characterizations of probably total functions, probably total NP functions in fragments of bounded arithmetic. And these characterizations are of increasing complexity. We cannot show that they are of increasing complexity indeed, but at least formally they are of increasing complexity. Unfortunately, we are still not able to prove that at least in relativized world they are of increasing complexity. So this is one of the big open problems in proof complexity, to show that that this hierarchy of total function NP problems is increasing. This is something that is not hopeless. I believe that it only requires proving some very complicated switching lemmas, but so far nobody was able to do this. Like with the set of tautologies, we also have a similar connection, which are disjoint co-NP, pairs of disjoint co-NP sets. Again, polynomial reductions and Turing or many one are defined in the same way. And we can state the conjecture that there is no complete disjoint co-NP pair. Again, it's a syntactic class, so this is equivalent to, if true, then there is no fixed theory that proves disjointness of all co-NP pairs. And we have a similar connection as before, namely that the conjecture about disjoint co-NP pairs implies the conjectures about total function NP problems. So the situation so far is that we have two branches of conjectures. One is about tautologies and disjoint NP pairs, and another is about total function NP and disjoint co-NP pairs. But SAT is still missing, and you can now guess where SAT is. It's not not obvious, so we will look at SAT. So I want to spend a bit more time with SAT because this is a program in SAT, at Simons, which is focused on SAT. So SAT is, of course, very much different from TAUT, but we also can consider proof system for SAT. And a proof system, what is a proof system for SAT? It's just any evidence that proves that a formula is satisfiable. What are polynomial simulations? They are exactly the same as for TAUT, that you transform proof in one proof system into another into a proof in another proof system in polynomial time. But the difference is that there is the standard proof system, one very special proof system, and this is just satisfying assignments. If you want to show that a formula is satisfiable, then the best you can do is to provide a satisfying assignment. And this proof system is polynomially bounded. While we believe that there is no polynomial bounded proofs for tautologies, we have a trivially polynomially bounded proof system for SAT.
Well, I'm sorry for interrupting. If we're really running over time, but if you could take a couple more minutes.
Oh, sorry. I thought I was.
I'm sorry. We've been quite relaxed, but just realized it's sorry.
Okay, I don't have many slides, and I'll skip something, so I will finish. 5 minutes, or is okay, or?
Oh no, sorry for that. I just looked at the clock. Oh.
Yes. So okay. So we so the situation is different, but still there may be proof systems that are not polynomially bounded. Now, an example of a proof system for SAT that is probably not polynomially simulable by the standard proof system is the following one. You take the standard proof system and you add basically factoring into it, which means that you take as a proof any satisfying assignment, or if the formula expresses that n is not a prime, then n will be just the proof of this. And it is not difficult to see that if factoring is hard, then the standard proof system does not polynomially simulate the system, because if it did, then we would get a satisfying assignment for formula phi, and this is what we believe is not possible. All right, so let me quickly go over this natural proof system for SAT. You can get natural proof system for SAT if you realize that phi is in SAT if the existentially quantified formula as a quantified tautology is a quantified tautology. And then you can use proof system for quantified tautologies. And you have to go faster. What is interesting is that the standard proof system polynomially simulates the G star 1. I'm not going into the details about it. And the point is that is the witnessing theorem of Cook. So the bottom line is that if you have a witnessing theorem in a proof system, then it essentially means that the standard proof system polynomially simulates it. Okay. If there is an optimal proof system for SAT, then there exists a complete problem in total function NP I wanted to prove this, but I don't have time, so it's a pity because it's a simple proof. So let me finish by saying that we can state a conjecture that SAT doesn't have an optimal proof system, and and the proof that we skipped gives us that total function NP conjecture implies the SAT conjecture. So we can place SAT into the diagram, and it is between P unequal NP and total function NP conjecture. Now, and these things have been ratified. So we know that many things are different. In particular, these two branches are really distinct branches. But unlike showing these implications, which are usually easy and more or less straightforward, relativizations are pretty technical and complicated. So we still don't know whether these two are different and these two are different. Okay, thank you.
Thank you so much, Pavel. This is really, really interesting. Okay, we are running a bit over time, but maybe
Moshe has a question.
Okay.
Just a quick question.
Yep.
So Harvey Friedman has this program showing that these stronger set theories end up proving kind of you need strong set theory to prove very mathematically looking statement about kind of numbers, just statement about number theory and things like that. Mm-hmm. And I wonder whether you can use his program to show that these stronger set theory, like strong cardinal axioms, prove things that actually they have computational meaning.
I wish I could, but I cannot. Yeah, so the problem is that essentially what we are able to do is just somehow to rephrase the consistency in some combinatorial way, but it's not anything that can be interpreted as a statement about computational complexity. But this is well, I would like to do it, and I'm thinking about it, but I don't know how to do it.
Thank you.
Yes, thank you so much. And maybe while Shai is setting up, if anybody has any more questions for Pavel, and thank you so much, Pavel. This is fantastic. This is really interesting.
Antonina, may I ask a question?
Mm-hmm.
Pavel, thank you for the talk, first of all. My question is the following. Consider the conjecture that that NP intersect co-NP, which is a semantic class, has no complete problem. Where would this conjecture fit in your diagram of connections between the conjectures?
This doesn't fit into any of the branches, so it's in the middle. It's stronger than, of course, P unequal NP, but it's in the middle. So we are. I'm not sure that we can show by relativization that it is not in any of the branches. Maybe Irfan Khaniki, if he's connected, can tell you more. But it seems that this is in between.
Thank you.
Thank you so much.
It's possible that there is a third branch which is based on this, but I don't know other than this problem in this direction. So sorry for being a bit longer than I expected.
Oh, I'm sorry for kind of making it more loose than needs to be. Thank you so much, Pavel. This has been beautiful.